Hello, everyone. I'm Ryan Wright. I'm the founder and CTO at ThatDot. And today I want to talk to you about graphs, which are for stream processing now. So to back up a little bit, it's nice talking to an audience like this because we probably have a lot in common. We have a history of having done our analytics at the end of a stream. So you might do all kinds of work to set up a data pipeline to ingest your data in real time. But when it comes time to understand that data, the understanding piece has to sit at the end, because that's where we can collect all the data together and we can process it, put it together, understand what it means and connect it and go from there. But by that point, we're done streaming. And now this is a static batch processing operation at the end of the line. So this is the old way of doing things. And it's nice to kind of come out of that world into a more modern approach where we can finally start focusing on the kind of analytics that you can do while the data is flowing. But even when you live in this sort of a world, the analytics at the end of the line can still be pretty challenging. And recent years, recent decades even, have seen improvements of new tools and all kinds of interesting things you can do at the end of the line for batch processing. And part of what we're going to talk about today is the kind of batch processing you do at the end there that often takes the shape of like a graph. Being able to take in one event at a time from your stream, stitch it together into a graph, can give you new kinds of insight and help you solve certain kinds of challenges that are really difficult. Even in just static batch processing land. But today, what we're going to talk about is that sort of problem solving with that graph-shaped problem at the end, but doing it upstream in a stream. So when we talk about graphs and streams, there's kind of two different mindsets that you may have in mind. So on one hand, the graph database world has done a good job of kind of teaching us how to think about data as a graph. So where each record that streams in might represent a node or maybe a couple nodes. Those couple nodes then have relationships to other nodes. You could think of each node in a graph as being like one line in a relational database. And so each record then produces a node and has its relationships explicitly recorded in the data. Recording those relationships makes it really insightful. You can see a lot of things that otherwise are only the result of joining a bunch of tables together after the fact. But when you write those relationships in while data's coming in, you get this really insightful connected structure that helps you solve a lot of challenging problems. So on one hand, when we think about graphs related to streams, for a long time, graphs have kind of sat at the end of the data pipeline, like we were talking about a moment ago. And then that's where the data gets built into a graph. But depending on your background and depending on kind of systems you may have built in the past, there's another way in which graphs show up in the stream processing world. And that's really as the stream itself being the graph. If you've built data pipelines, it's common to have microservices that each do a little job, but where data flows in from some streaming sources, goes out to some microservices, does some work, comes out of each of those services into some others, might flow apart and be spread out, might come back together for centralized services. And in that way, the stream itself becomes a graph. And building a stream is all that deep work of trying to figure out what is the job you have to do and what is the processing that gets you to accomplish that job along the way. But the stream becomes like the railroad tracks. It's that on which the data flows as it's coming through the streams being delivered at different microservices. What we're going to talk about today is an open source application called Quine, which actually lets us take these two separate ideas and merge them together. Quine is the world's first streaming graph. And the whole idea is that it can do that sort of graph processing in the stream. So you don't have to hold it and wait until the end when everything stops moving, but you can actually do that data processing while it's still flowing. And while graph databases have gotten a little bit better recently, they're still far, far from being able to do real-time processing in high-volume data streams. So what Quine is really good at is building this graph in an event-driven way that keeps the spirit of all the stream processing tools and philosophies and ways in which you work with real-time streaming data. but then gives you this graph layer to process and solve those kinds of challenges while the data is still flowing. So what makes a streaming graph is really that data streams out. Not only does it flow in from your typical streaming sources like Kafka or Kinesis or Pulsar, but it also flows out, often to those same tools. Or maybe it goes out to other analytics tools like Pinot or other kinds of services that you may set up for downstream processing. So data streaming out is the key capability. What enables that in Quine is something that we call standing queries, which we'll get into here in a moment. But first, let's pause for a moment and step back and say, why even a graph in the first place? Well, behind the scenes here, every streaming solution has to come up with some answer to this really thorny question about basically doing joins on a stream. So how do you join what would be tables when your data is flowing through? And really, if we start with a stream of data, there's probably different kinds of things in it. You've got your A's, B's, and C's. And our goal is to put those pieces together. You can kind of think of this like a self-join. If the stream is a table, you're joining it to itself. But what makes this challenging for stream processing is you're joining it to itself over time. And so there's the history of what you've seen before that you need to have in order to understand, well, what do I do with the next thing? And the typical approach is to say, we're going to plug into the stream and we're going to build up some queues. We're going to hold on to all the different types of things that we might see, because our goal is to put the pieces together and be able to emit an ABC, to send downstream to whatever the next service is, a combination of A's, B's, C's that are combined in just this way. Since we're only getting an event one item at a time, we've got to hold on to the A's somewhere, we've got to hold on to the B's somewhere, we've got to hold on to the C's somewhere. And so as we get one of those, they're stored in some queue of unmatched events. And then every time we get a new record, every time we get a B, we go look at all the A's and say, do we have the right match? And if we have an A-B combination that matches, great. We're on our way toward making the whole pattern. But we've got to hold on to that A-B combination. Or maybe it's a B-C combination because data arrives out of order. So we hold on to the B-C combinations. And we start building queues and queues and queues of unmatched events that build toward partial results. And this ends up being a pretty thorny problem, especially as your pattern gets larger and larger and larger. You have this combinatorial explosion of how many of these queues you have to maintain. So the implications of this means that most data engineers have to kind of accept an undesirable compromise to say that, well, we can't have infinite amounts of RAM. We can't have queues that hold on to stuff forever. So we'll set limits to how big these queues are and probably set by how much RAM we have available. So that's how much partial data we can hold on to. And that'll be our time window. We'll let old results fall off the end of the queue and we'll just lose those and just accept the fact that we can't find anything that might have been matched later because we don't have infinite RAM. We can't hold on to the entire stream. So instead, we hold on to time-windowed versions of queues at the expense of losing some of the matches that we would have found if we could have bigger time windows. The other alternative is you might store these things instead of just holding them in RAM, which would be fast and nice. You might use a slower solution where they're stored more durably and can actually grow to larger sizes. So maybe you set up key value stores to hold on to these queues. But now the problem becomes whatever pattern you're looking for gets encoded in the architecture, in the number of key value systems you set up. And the relationship between these things has that same combinatorial complexity. So we're still building large queues. Maybe they're larger, so our time windows get bigger. But now the pattern of these queues that could have been held in RAM are now spread across systems and the architecture of the whole pipeline. That might work, and it might work for a while until we need to change it. And as soon as there's a change that's needed to the pattern we're looking for in the end, we have to upend the entire architecture. A new pattern means we have to redesign the architecture of the pipeline. And so this is a thorny problem, and it tends to start out with some smart engineers who can find a way to solve this. But then over time, it grows and evolves, and you end up with an architecture that kind of looks like this. We've got data coming in on one side, and the goal is to transform that data into the business value, the purpose for why we built this pipeline in the first place. But in the middle, we end up with this complex network of microservices with implicit interdependencies, and what might start as a good solution evolves over time as people come and go from the teams and turns into a really thorny problem. But hey, this is technically possible. We can do this. Smart teams can spend, enough time to go build these kinds of systems, and it can work. But if you've built one of these before, you've probably also seen it come crashing down in flames, because this is hard, it's error prone, it takes a really long time to build these, and it's expensive because you need people with a ton of experience to be able to do this right. And if any of those people start leaving the team, then you're probably better off rebuilding it from scratch instead of trying to make some small little changes over time. And somehow this has kind of become the normal way in which we build real-time data processing to get to the analytics and business value for which we're building this pipeline in the first place. So what we're talking about today is an alternative here. Quine is an open source streaming graph that can live inside that data stream, can plug into those streaming sources, and then can help untangle that big mess in that streaming join problem of how to put the pieces together so that you can find what matters, get the patterns that you need, feed the downstream components that need to consume those, and get your answers in real time. Quine supports plugging into all kinds of different tools, lots of streaming tools, and it's usually streaming in and streaming out. The way that it solves that streaming join problem, internally, it manages a graph that stores its data in a durable store that looks kind of like a key value store, but can scale horizontally, like with Cassandra or ScyllaDB, to grow with the size of the data for any volume of data. So you don't need to limit to just small time windows. You can actually join across and build these complex graphs that find all the important results and do it over huge amounts of data and still maintain those real-time guarantees about how quickly we can get to the answers. Using Quine is really a two-step process. On one hand, we've got streaming data coming in. It might be log events, it might be alerts from other systems or metrics or any other kind of data. It might be click streams, or it could be cryptocurrency transactions, any of that kind of data coming in as a stream. And step one is define an ingest query using the normal Cypher graph query language, an ingest query to structure that into a little shape in the graph. A small little piece of the graph that will end up overlapping other pieces to build this rich, expressive structure. Second piece of the puzzle is what we call standing queries. Also, just a Cypher query that defines what you want to find. Here's the shape of the thing that I'm looking for in the graph. Monitor the graph while it's changing in this event-driven, efficient pattern so that every time I get a new result, it can stream out immediately to the downstream systems that we need. Well, that's still a little abstract, but two-step process: ingest and build the graph. Second step is monitor the graph for the patterns that matter and stream them downstream. But if you want to learn more and see some concrete examples of this, we've got a long list of recipes that actually embody specific examples. So lots of different purposes and uses, different kinds of analytics being done, different kinds of jobs being done. Each of those is all wrapped up in a recipe that from start to finish, you can run with a single command line and stream out those results to see how it works. Then you can tweak the recipe if you want to, turn it into your own solution to your own shape of problem. All of these are available on the open source website at quine.io/recipes. But what I'd like to do now is pick one of these recipes and let's dive in and show it so we can see a little more concretely what this thing really looks like. And for this example, let's look at streaming entity resolution. Entity resolution, if you haven't encountered this before, it's the problem of having to refer to data. You've got a lot of data coming in and it refers to things, stuff that you and I know is like one canonical thing. Like there's one city named Portland. That just happens to be the best city, but incidental to nothing, there's one city named Portland, Oregon. And any references to that sometimes might misspell it, might leave off the geography, might get confused with the other Portland on the other side of the country. That's the sort of entity resolution challenge that starts from data and what's coming in and figures out what are the real world objects that we're trying to refer to. So we need to resolve those many different references, even if there's typos and things like that, but resolve those many different references so that there's one record per unique entity that we're trying to refer to. And so in this example, we're going to look at using a streaming graph in Quine to apply some simple matching rules to real life data so that we can resolve entities in real time while data streams through. Now, the old way for doing this, what you'd normally have to do is you might start with Kafka. You've got data streaming in, and then probably that data goes into a database or into a data lake where it comes to rest and it stops streaming at that point. And it does so that you can bolt on ETL tools to come in and do this kind of work for entity resolution, maybe for other purposes too. But you bolt on those tools to a static data set. And what started maybe as a clean data set now becomes this creaky old, collection of data, but it's there. It's good. You can use it. Your users might not be the happiest people in the world, though, because now they have to come query, answer. It slows down. Everything kind of comes crumbling to a halt. Your data is no longer a stream. The entity resolution problem has forced you into batch processing from that point on. But there's a new way. If we use a streaming graph, we can start with that same Kafka data. Now let's stream it through into Quine so that data comes in real time. We connect it together. We understand its relationships. And Quine can use those standing queries to find resolved entities, stream out clean data in real time so that a downstream system like Apache Pinot, or if you have the StarTree souped up version of it, you can consume that in real time to do the analytics that you need on now clean data and continue on to happy users who get streams of insights one after another, and the insights keep coming as soon as they're available. So in this case, what I want to show you for this entity resolution example starts with some postal data. This is from a public data set from court records and referring to real life humans trying to type out real addresses. But sometimes there's typos and there's other challenges here. So we want to take address information that gets parsed out with something like libpostal into a simple parsed format like this. But we want to add in this feature along the bottom that lets us know how this one entity resolves into the canonical reference for that one physical place, the physical address. To do that, we use standing queries. A standing query monitors the graph while it's changing. So the left-hand side here, this is a cipher standing query. The yellow part highlighted on the left is kind of like ASCII art. The way cipher works, you draw the pattern you're looking for in the query language. So instead of saying select like you would with a SQL query, you do match. Match this pattern. We're going to look for a combination of post office box and postcodes. The relationships there tell us how to resolve two entities into the same one with this simple rule. But instead of just looking at text on the screen, how about we actually go see this live? So I'm going to leave the slides, flip over to a screen here where you can see the open source Quine.io website. So if you want, go download and you can follow along and do exactly what I'm doing here. You can download the jar or Docker container. It's a JVM application that just runs locally. I'm going to go ahead and run this locally so that we can see what it's like. Running a recipe is just a one command line argument. So Java jar, give it the latest jar and provide the recipe. In this case, I've got my entities recipe that we're going to run. That starts with that sort of postal information pulled from public records data. And it starts streaming in. We see counters of how it's streaming in. And again, it's just running locally on my laptop. So if you need to, you could run this on servers and scale it up. But running here on my laptop, let's go explore. I've got a record that comes in from the data stream. And this is one address record. If I want to, I can go look at its properties. I can see what's on here. And sure enough, it's address information, kind of like what we were talking about there. And it's unresolved at this point, but it's just a record pulled in, adding, say, a row in the database. But since this is a graph, we've actually got structure being built and connections being built. So if I explore what's adjacent to this, I can see the entity that's being referred to in that record. And if I want to, I can particular entity. But let's clean that up a little bit. That one entity might be the canonical one, but there's, as we saw, there's other records and maybe they refer to other things. In this case, just to skip to where this goes, I can go click for resolved entities and see all these other references that have been resolved by the rules encoded in a standing query, because this same information gets connected in a graph and lets me understand which of these things are actually referring to the same entity. Here's what I mean. If we look at the property subgraph, so just the features of that entity that came from the data, we can see it's in the city of Malvern, has a postcode, house number, state, and so on. We can explore other connections because now data intersects. These are other entities in the city of Malvern. Back up a step. There's other things. We could go explore Pennsylvania or postcodes or other things, and the graph gets really big really quickly. But what I wanted to show you is that we can just say, who else is this entity known as? And because of the entity resolution rules being done by the standing query, here's a list of all these other names. Same thing we saw with those dotted purple edges. So that's great. We can resolve entities. We can even see what's the canonical record that all these get referred to. Here's our canonical entity. And all the connections to that canonical entity are all the other names that would have been other entities, but are now resolved in this canonical way. But I told you this was a streaming solution. And so far, we're just this is like graph database kind of things. So let me just run this again. And let me show you what the standing query is actually doing. So one standing query does the connections and applies our entity resolution rules internal to the graph. But I'm going to clear it all out and run it again, because there's a second standing query that is producing a real-time stream of data coming out of this system. I'm going to tail that log just so we can take a look. And here's a real-time stream of resolved entities coming out of the graph processing that we've done. Pause this stream and take a look. We've got, say, one record built out of this much here. Here's a record. And now you can see it has this field added near the bottom of the record. It has a resolved entity that continues to stream out. So as soon as we've resolved that entity, a consumer like Apache Pinot or a Kafka stream can consume from this data, can continue on with its work downstream now that it has clean data to work from. So that's just one example of a recipe applying real-time streaming graphs to clean up data, to do hard work, hard jobs that are really tricky to do and require being spread out over big pieces of architecture across a whole data pipeline in that way. So we built this system so that it could be easily integrated into existing data pipelines. So let's say you've got some custom business logic and you'd like to wrap up or maybe make the next iteration of a certain piece of that, make use of a streaming graph. Well, it's easy to fold in to a small part of a data pipeline or alongside of some other logic. And then you can feed other analytics applications downstream now that you've cleaned up data, you've done some important graph processing. And critical to this problem, the Achilles heel for graph systems like this has been this challenge of scale. You build data pipelines because you've got a lot of data to work with to begin with. Well, Quine has been shown to scale beyond millions of events per second. So there's an enterprise version of this with additional enterprisey kinds of features that can run in a clustered fashion, can scale horizontally without limit, and it remains resilient even when encountering, say, system failure for host dying or database connection being interrupted or network partition, all those important pieces that happen in real life, those important features of resilience that a distributed system needs to maintain. And so this is meant as a robust enterprise-ready capability that can start small, go into an existing data pipeline, and can grow to solve big, important pieces of the real-time analytics challenge and help you clean up data or feed some of these other systems downstream. If you'd like to learn more, the open source website is quine.io. Quine is developed and maintained by a team of people at ThatDot, and we're hiring, by the way. So if you're interested in this sort of thing, let us know. But there's also a community on Discord. So if you want to get started, but you've got questions or you're not quite sure what to do and how to get going, check out the community in Discord or grab the open source code and let us know what you think. Thank you very much. It is an honor speaking to you all today. And I appreciate the chance to share what streaming graphs can do now for stream processing. Thank you.